Thank you all for coming out today. As Tim introduced me, my name is Anthony. I'm a student here, and I study theoretical physics. And my particular area of focus is on something I'm going to call quantum black holes. But before I can explain what that is, I want to ask a broader question, and that is, what exactly is it that we mean? What do we mean when we say scientists have a theory of something? A really common misconception here is that it's just some idea we have about how things should work. But the problem with that is that your idea has to be grounded in reality somehow. And it was actually the author, Mark Twain, who said it best when he said, "How empty is theory in the presence of fact?" Now, since I'm a physicist, I feel obligated to also put up a physicist picture here. So I went with Richard Feynman, theoretical physicist that you may have heard of. And he's quoted as saying, "The test of all knowledge is experiment." And what both of these guys are trying to get at is that a theory isn't just some empty idea. It's an explanation for a physical process that has to be supported by experimental evidence. If you have an idea about how some process in the world should work, but you don't have any kind of experiment to back it up, you can't really call it a theory from a scientist's point of view. Now, there's two theories I'm going to be talking to you all today about, and that is quantum mechanics and general relativity. Now, quantum mechanics is this theory that says that when we go to really small scales, like microscopic sizes, the universe starts getting really lumpy and discrete, and everything's made up of tiny little particles, and these particles form together to make up all the matter we see around us. General relativity, on the other hand, is Einstein's famous theory of gravity that applies at really big scales. I'm talking distances the size of solar systems and galaxies, and it explains how gravitation works on these scales. Now, when I say that these are both theories, I mean they're both backed up by experimental evidence. For quantum mechanics, the best test that we have comes from the Large Hadron Collider at CERN, also known as the LHC, where it's a facility that smashes together particles at incredibly high energies. These particles come in, they interact with each other, and out comes this spray of particles. And what I've pictured here is a simulation of one of these particle spray events from one of the detectors at the LHC. Now, what happens is they measure properties of this spray of particles, and they figure out if the properties they measure match with the theory. And as far as we can tell, they match really precisely, telling us that we have a pretty good theory for how physics works at the small scale. For general relativity, we also have a lot of experimental evidence. There's how the planets orbit around our sun. There's this idea of gravitational lensing, where light actually bends around really heavy objects in the sky. And more recently, there's actually gravitational waves, which are these little ripples in space-time that result when supermassive objects orbit around each other. This last one's interesting because Einstein actually predicted them in 1916, but it wasn't till last year in September that they were actually detected for the first time. So it was actually kind of impressive. But what I'm trying to get at here is that both of these theories predict a lot of different things, and we can do experiments to confirm these predictions. The problem, though, is that they're separate theories. They apply at different scales. Quantum mechanics is at small scales, general relativity is at big scales, and we don't have a good way of meshing them. And in particular, this is weird because gravity is, for some reason, singled out. All of the other fundamental forces we know of work at the small scale, but for some reason, we only understand gravity at this really big scale. So to understand why this might be a problem, I'm going to compare gravity to something we're all a little bit more familiar with, and that's light. So we all know how light works at big scales. If you take some kind of light source, like a flashlight or spotlight, and you shine it, you know that light rays are going to come out, and they're going to illuminate the surface that they hit. If you were to actually zoom in on the light and go down to the microscopic scale, though, what you'd find is that it's not just these continuous light rays. It's actually made up of lots of tiny little particles that we call photons. And so we have two different ways of looking at how light works. We can look at this macroscopic scale and see how it works at large distances in terms of light rays, or we can zoom in on the microscopic scale and understand them in terms of these photon particles. Now, we'd like to be able to do the same thing with gravity. And we understand how it works at big scales in terms of general relativity, but if we were to try and zoom in on this, we'd be very confused. We don't actually know what's happening at the microscopic scale for gravity. We'd like to think that there's some kind of particle that carries the information about gravity, some kind of graviton, for instance, but we really don't know. And this is a problem that's been plaguing physics for a really long time now, kind of this idea that we'd like there to be some kind of quantum theory of gravity, but we don't know what it is. Now, what you all might be thinking at this point is, okay, well, if you don't know what it is, why don't you do some kind of experiment to test it? After all good theories are supported by experiments. Well, the problem with this is that gravity is actually a really weak force. And you might not think that at first, but there's actually an example in all of your homes at home. I'm sure you guys all have a kitchen with a refrigerator in it, and on this fridge you might have magnets stuck to the outside of it. Now these magnets are tiny little objects that are generating a very small little magnetic force, and yet this tiny little magnetic force is enough to keep them suspended on the fridge, despite the fact that we have this gigantic Earth beneath us that's pulling down on the magnet as hard as it can with gravity. So what that tells us is that for some reason gravity is much weaker than other forces that we know of in nature. And this makes it really hard to do experiments. So for light, if we wanted to test light at the quantum level, we'd need some kind of light source. We'd shine this light source on a detector, like a solar cell or something like that. Photons come out of the light source, they hit the detector, and they interact with the particles inside the detector. We measure these interactions, and we measure the properties of the photons that did this, and we can learn about photons at this quantum level. And we're actually really good at doing this. We've actually constructed devices that can measure up to 100 million photons every second. So this is impressive. We really have a good understanding of what's going on at the quantum level for light because we can do these really exceptional experiments. For gravity, however, if we wanted to do some kind of experiment to test quantum gravity, if there's some kind of graviton, we'd need a detector, first of all. So some kind of object for the gravitons to interact with. And we need a source for the gravitons. In this case, though, it'd be some kind of really heavy object, like a star or a planet, because we know that gravity is this interaction between massive objects. Now, if I really wanted to make sure there were a lot of gravitons coming off this, I'd want this source to become really, really massive, in the same way that I would turn up the flashlight's brightness if I wanted to see a lot more photons. So let's just pretend that my graviton detector is orbiting, I don't know, the heaviest star in our galaxy. And just for fun, let's make my detector the size of Jupiter, just to make sure that it's as big as possible, that none of the gravitons are going to miss the detector. They're all going to hit it, and we're going to learn something about quantum gravity. Well, the problem with this is that if we do our calculations and we factor in how weak gravity is compared to all the other forces, we find out that according to our best estimates, we'd measure maybe one graviton every 100 years, which is insane. This clearly isn't a feasible experiment. Grad students are only in school for about 7 years, so you can't force them to do this. So we need some kind of other option. So the question is, what do we do now? Well, the first option is that we just give up. We say, this is too difficult, I'm going home, going back to bed. But I think I'd be a pretty bad physicist if I went with this option. And I think my advisor would be really unhappy with me if I did this too. So what I'm going to do instead is I'm going to get creative. And in particular, we're going to look for places where the small-scale quantum physics is just as important as the large-scale general relativity physics. And as you may have guessed, the place where this intersection occurs is in black holes. Now, you may or may not have heard of black holes before, but just to make sure we're all on the same page here, I'm going to define black holes for you as a region in the universe where gravity is so strong that nothing can escape past the boundary, also known as the horizon, of the black hole. Now, to demonstrate this, I've drawn you all a beautiful picture of a black hole, and I've drawn the horizon of the black hole in red outside of it. Now, black holes aren't actually red, but this is just for the purposes of this demo. Now, if I have some kind of object sitting outside the black hole, this object is free to go in whatever direction it wants, as long as it has enough energy. It can go up, down, left, right, wherever. But as soon as this object crosses past the horizon, if you figure out which paths this object's allowed to take, it turns out that all of them just take it further into the black hole. The force of gravity is so strong that it pulls it closer and closer to the center of the black hole, no matter what it does. And this is why black holes are called black. Nothing can escape past the boundary, including light. So we really shouldn't see anything coming out of them. Now, I want to emphasize that everything I've been talking about right here is purely in terms of general relativity and gravity. I haven't said anything about quantum mechanics. These are objects that were predicted and we can actually describe really well just using general relativity. But a really famous physicist by the name of Stephen Hawking in the 70s asked a really good question. and he said, what happens if I put quantum mechanics next to the boundary of this black hole? And in particular, he studied a really weird quantum mechanical effect called particle-antiparticle creation. And what it is you start off with sort of just nothing, there's nothing in front of me, and spontaneously, out of nowhere, you can have a particle and its antiparticle just pop out of nothingness. These particles are then free to move along, they drift a little, they do their thing, but eventually, they're going to come back together. And when they come back together, they collide with each other, and they end up undergoing particle-antiparticle annihilation, where they disappear back into nothingness. And this is a really strange effect, but we know that it happens. And the reason that it's okay is because it happens over such short distances and over such small periods of time that we don't notice it. It doesn't affect any of our day-to-day activities. It's just this really strange thing happening in the quantum world. What Stephen Hawking asked, though, is what happens if I put this next to a black hole? So the first step is the same. I have a particle and an antiparticle pop out of nothingness. But let's say that one of them happens to fall into the black hole. Well, they move along. The red particle is now stuck inside the black hole. And they'd like to recombine and annihilate back into nothingness, but the red guy is stuck. So the blue particle doesn't have his buddy to collide with, so he can go wherever he wants. He's free to go jet off away from the black hole, and he ends up actually escaping from the black hole. So what this means is that if we put quantum mechanics next to a black hole horizon, we should actually see a bunch of particles just shooting away from the horizon. And this is a process known as Hawking radiation, named after the physicist who first came up with the idea. So what this tells us is that black holes are actually constantly emitting, they're losing their energy by Hawking radiation all the time. And what this actually tells us is that quantum effects are really important for black holes. Now, I have a demo here that I want to use to sort of demonstrate this. I couldn't bring in a black hole for you guys, but I have the next best thing. I have, on this side of the table, I have what is pretty much an ordinary light bulb. And on the other side of the table here, I have a detector. Now, what I'm going to do is I'm going to turn on this light bulb, and I'm going to start pumping electricity into it. Now, what's happening here is that the electric current is running through the little metal filament in the bulb. And the electrons in this path are colliding with all the particles that are inside this metal filament. And these filament particles are getting excited. And when they're excited, they have lots of energy. And then they release that energy in the form of photons, or light. This light, or these photons, comes over to the detector, and we capture them. And we learn information about them. So what I'm plotting here is the information coming from the detector, where you can see that on the left and right axis, we have the wavelength, which is related to the energy of the photons. And on the up and down axis, I have the number of photons we're detecting. So right now, we're capturing something like 1,500 photons per second at the peak. And they have a wavelength of roughly 600 nanometers. Now, what happens if I turn down the electricity here is that you start to see this peak go down. The number of photons that I'm detecting decreases by a huge amount. And in fact, if I zoom back in on this new peak, you can see it's way lower. I'm getting not even 200 photons a second at its peak. And in fact, what's interesting is that the peak is shifted. The photons now have a wavelength closer to 700 nanometers than the original 600 nanometers. So what this means is that by turning down the electricity, I'm giving the particles inside the light bulb filament less energy. And that actually ends up changing the properties of the radiation that you see coming out of the light bulb. So what this is telling us is that it's the actual quantum system inside of this light bulb filament that determines the properties of the radiation that's coming out from it. And this is a pretty universal feature in physics, that when you have radiation, it's indicative of some kind of quantum system that's causing this radiation to appear. And the same is true for black holes. That is, we should be able to describe the black holes at some kind of quantum level. So I call this quantum black holes, because we know that they have this weird property of Hawking radiation coming out from them. But what's important to keep in mind is that even if I had some kind of idea of how to describe black holes at the quantum level, I still understand black holes really well in general relativity. So now I sort of have two different ways of looking at black holes. There's the way in GR, where I know exactly what black holes look like, I know their properties, and I can study them well. But now I want to be able to construct black holes in some kind of idea that I have about how quantum gravity should work. And this gives me a really good check on my idea of quantum gravity because it's not allowed to contradict all of the results in general relativity. We know that general relativity is a well-established theory, so I'm not allowed to break that. So if I give you an idea for how quantum gravity works, and it makes black holes look totally different than they do in general relativity, I know that my idea is wrong. It doesn't pass this test. I need some kind of idea for how quantum gravity works that gives me the same black holes that I know that I should get from general relativity. And this is what leads us to the conclusion that we can think of black holes as some kind of laboratory for testing ideas about quantum gravity. It's not a laboratory in the typical sense where I do experiments to measure properties, but it gives me a way to check that my ideas about how quantum gravity should work are correct, or at least not wrong. So this is what a lot of my research focuses on. I study black holes and general relativity and quantum gravity, and I try to do sort of this matching procedure to make sure that my results are consistent. And in particular, I study a property of black holes known as their entropy. Now, the really technical physicist definition of entropy is that it's a measure of the number of microstates or configurations of your system. And really, this is just a fancy way of saying how many ways can I build up my system. So to do this in person, to run through what this, to demonstrate this, I have a little demo here. And in my demo, I have two particles, particle A and particle B. If you want, we can give them names. So let's say this is Alice and this is Bob. And I have two systems to house them in. System 1 has 2 slots, and that's shown on the camera right now. And system 2 has 3 slots. Now, if I tell you that I have to put both these particles inside the system, and they're not allowed to occupy the same box, then there ends up being exactly 2 ways to configure these. I can put Alice in the first slot, and Bob in the second slot, or I can swap them. And obviously, there are no other ways that I can do this. So I have 2 microstates available to my system, 2 different ways to build it up. If I were to swap this out for system 2, though, you can see that there's actually a lot more ways to configure my particles. I can swap them around, I can move them between the second and third slots, I can do any number of things. And if I count all the ways that I can actually arrange these particles, I find that there are 6 total configurations. So I conclude that there are 6 microstates for the system. So if I compare this, I see that the number of microstates available to system 2 is bigger than for system 1. And so I conclude that the entropy of the second system is bigger. Now, this is a really good way of understanding entropy if you understand the quantum mechanics behind your system. This method required me knowing that I have 2 different particles. It required intimate knowledge of how they can go into the boxes and how to arrange them. But what happens if I take these particles away? What if I say, okay, there are particles inside of here, but you can't see them, you don't really know what's happening at the quantum level? Well, even if I take the particles away, you can obviously see that system 2 is bigger than system 1 in size. And what you can intuitively think is, well, I don't know what's happening at the quantum level, but since system 2 is bigger, there should, roughly speaking, be more room inside of it for these particles to configure. There should be more space for these particles to stay in and more ways to arrange them. And so that ends up leading you to the same conclusion, that even though I'm looking at this at sort of a macroscopic scale, zoomed out, I don't know anything about the particles, because the size of one system is bigger than the other, its entropy should be bigger too. So this gives us 2 different ways of looking at the entropy. We can look at it quantum mechanically in terms of the number of microstates, or sort of at a larger scale in terms of size. And this is why entropy is a really good property to study for black holes, because we want to be able to compare the quantum world and the general relativity physics. So just to sort of sum this all up, remember we have 2 theories. We have quantum mechanics, we have general relativity, where quantum describes physics at small scales, general relativity describes gravity at these big scales. And they're separate theories. And that bothers us for a lot of reasons, and we'd really like to be able to understand how to unify these. So we studied Hawking radiation, and we learned that I should actually be able to describe black holes in both theories. I should be able to look at black holes in general relativity or in quantum mechanics. And in particular, I'm going to look at the black hole entropy in both theories. In the quantum mechanical language, the entropy is the number of ways that I can actually configure my quantum system inside the black hole. Whereas in general relativity, it's pretty much given by the size of the black hole. So this gives me a really interesting window between these two theories, because I know in order for my idea of quantum gravity to be correct, it has to match up with the result in general relativity. And this is a really powerful result because it gives us a really great check on ways that we might unify quantum mechanics and general relativity. So hopefully this field of study is going to give us some really great insights into this unification in the near future. I'll let you all know how that goes. So with that, I want to thank you all for coming out. I'd like to thank the organizers of this event, the demo lab in particular, and I'd like to thank my family, friends, and my girlfriend for being here and supporting me in my endeavors. So with that, I'm going to give the mic to Marta.
So good morning, everyone. Thank you all for coming. My name is Marta. So I'm going to be talking to you about spintronics today and what that means and what it means for the future of computing. So before I get into the future of computing, though, I want to talk about the past and the present of computing. So you guys know how computers work today, so I can tell you how a spintronics computer would be different. And so you know the problems and challenges that we're facing with computers today that maybe spintronics can help us resolve. So the fundamental building block of a computer nowadays is something called a transistor. So I would say that a transistor is one of the most important inventions of the previous century because they're the reason that you can have so much computing power in something as small as your cell phone compared with the giant room-sized computers from back in the day that used vacuum tubes instead of transistors. So what a transistor is fundamentally, it's a switch. It's something that a computer can use to encode all its zeros and ones. So depending on the state of the transistor, it can be in a 0-bit state or it can be in a 1-bit state. So the way this works is each transistor has an input, an output, a switch at the top, which I've shown with the big orange button, and then an insulating region in between the input and the output. So if we were to run a current through this transistor, we would get a flow of electrons, and the electrons hit that insulating region, and they stop. They can't go through that region. And so if we were to try to measure an output from this transistor, we wouldn't measure anything. So now we say that this transistor is in a 0-bit state. But the crucial thing about transistors is that they're made out of semiconductors, usually silicon. And the cool thing about semiconductors is that it's very easy to switch them from being conducting to being insulating and vice versa. That's where the name semiconductor comes from. And so, for example, in silicon, we can use an electric field to turn insulating silicon into conducting silicon. So in our little cartoon, I'm going to demonstrate that by pushing this big orange button at the top of the transistor. That insulating region has now turned conducting. So if we were to apply a current, the electrons could pass through without any problem. And so in this case, we can measure an output. And so now we say that the transistor is in a 1-bit state. So in a real computer, these electrons might then flow on through the next transistor, or they might go to press the button on the next transistor. So in this way, all the transistors in your computer are interconnected in order to do calculations from things as simple as addition to more complicated things. The way transistors are arranged in your computer are in chunks called memory. So there are two types of memory in your computer. There's long-term memory and short-term memory. So long-term memory is where all your files and photos and Word documents and all that stuff are stored for long-term storage. So this consists of things like your hard drive, your CDs, flash drives. And the important thing about long-term memory storage is that it's what we call non-volatile. That means that you can turn your computer off and on again, and your data is still there, as you would want it to be. The problem with long-term memory, though, is that it takes a lot of time for your computer to access data in long-term memory. And so if you're actively using that data, say you're editing your Word document or you're photoshopping your photos, your computer doesn't want to have to access it directly from long-term memory. So what it'll do is it'll take the chunk of data that it's interested in, move it from long-term memory into short-term memory. So short-term memory is usually of a type that we call random access memory, or RAM. Some of you may have heard this. So the useful thing about short-term memory is that it can store the data that the computer is actively using. And so that means that your computer can access data from short-term memory very quickly. The problem with short-term memory, though, is that it's volatile. So if you turn your computer off, you lose that data. So at the end of the day, when you're done editing your Word document, your computer needs to move all that data back into long-term memory. So at the end of the day, your computer is continuously shuttling information between long-term and short-term storage as needed. And these are two physically separate memories on your computer. So this adds some complications in terms of building a computer architecture, or you have to account for the time and program your computer to shuttle information back and forth. So for the rest of the talk, I'm going to be talking mostly about different types of random access memory, so different types of short-term memory. So first I'll describe how random access memory works nowadays in your computer, and then I'll talk about a spintronic random access memory and how that has some advantages. So the main type of random access memory that you'll find in your computers is something called dynamic random access memory. So this consists of one transistor and one capacitor per bit. So a transistor is what I just described a few slides ago, and a capacitor is basically like a box to store charge. So that means that any calculation that your transistor did before, that information gets saved for a little bit until the next transistor is ready to use it. So the useful thing about dynamic random access memory, or DRAM, is that it's cheap and dense because it's simple. There's only 2 components per bit. The problem is that the capacitor is a pretty leaky box. It only stores charge for 65 milliseconds, which means that 20 times a second this bit needs to be refreshed. But what I mean by refreshed means that your computer needs to read the bit and then rewrite it. And since your computer is using a lot of time and energy just refreshing bits, not doing new calculations, that means that dynamic random access memory is still relatively slow. And you have the same problem that you have with most types of random access memory, that if you turn your power off, you lose your data. So at the end of the day, you do need some sort of long-term storage to keep your data safe. Now, the other type of random access memory that you'll find in your computer is static random access memory. So this consists of 6 transistors per bit, so it's a bit more complicated. I couldn't make a cartoon for it. But the advantage of static random access memory is that the 6 transistors are arranged in such a way that you never lose that data as long as you keep your power turned on. So since there's no need to refresh, static RAM is faster than dynamic RAM. But since there's now 6 components per bit, it's more expensive and less dense. And you still lose your data if you turn your power off. So in your computer nowadays, you'll have some combination of dynamic and static RAM. So most of your calculations are done in dynamic RAM because it's easier to make a lot of it, and it's cheaper to make a lot of it. But if your computer really needs to do a calculation very quickly, it'll do it in the static RAM component of your computer. So this is the current state of computing. This is what all your computers nowadays look like. The question is, how can we improve them? Because everyone wants to buy a new computer every year that's a little bit faster and a little bit better. So every single talk that you'll ever go to about the future of computing will have this next slide, the slide about Moore's Law. So Gordon Moore, who's the guy who founded Intel, predicted in 1965 that the number of transistors on a chip will double every 2 years. Now, computers aren't getting any bigger. If anything, computers have gotten smaller. So what this really means is that the size of the transistor is decreasing every 2 years. So I have here this graph of what the size of the transistor has looked like over the past 40 or 50 years of transistor-based computers. So back in the day, when the first computers came out in 1970, a transistor was about 10,000 nanometers wide. And to give you a sense of scale, that's about 1/10 the thickness of human hair. So already from the first days of computing, transistors were already very tiny. You can see why they had such an advantage over the much larger vacuum tubes. But transistors have gotten a lot smaller very quickly. Already by the time we reach 1990, transistors are about the wavelength of light. And what that means is that you're already at the limit where you can no longer see transistors, because if something is smaller than the wavelength of light, you can't see them even using an optical microscope. Now, this last filled-in dot that I have there is the last level that has been reached, and that's the one that was released in 2014, the 14 nanometer node. And 14 nanometers is ridiculously tiny. It's to the point where you can start counting individual atoms in each transistor. So specifically, 14 nanometers corresponds to 126 silicon atoms. So all of your transistors in your computers nowadays are at most 126 silicon atoms wide. And that's the total size of the transistor. Transistors have smaller parts within them. So there are some parts in your transistors now that are only 1 or 2 atoms thick. And so this plot is on a log scale, which means that it's not just a matter of shaving off a couple of atoms each time you make the next generation of transistors. We have to get rid of about 1/3 of the atoms in our transistors in order to reach the next step. So, for example, these 3 circles that are not filled in are the goals that the semiconductor companies have set for themselves. So the next one that's supposed to come out this year is the 9 nanometer node, and that corresponds to only 90 atoms wide. And then in 2018, they're supposed to be down to 63 atoms per transistor, and in 2020, they're supposed to be down to 45 atoms per transistor. And if we keep this trend up, by the time we reach 2050, we're down to 1 atom per transistor, which is, I mean, it's impossible. You can't build a transistor out of 1 atom. And so we're going to have to come up with some way of making transistors better besides just making them smaller and smaller. And there are other problems to making smaller transistors besides just how physically impossible it is to make a single atom transistor. One problem is that every transistor has some power loss associated with it. It's impossible to make something that's 100% energy efficient. So if you have smaller transistors, they're more dense, which means you get more power loss per unit area, which means that you get more overheating and lower energy efficiency. And that's obviously something that we want to avoid. The other problem is quantum mechanics. So I'm sure all of you Saturday morning physics regulars have been to many talks about how cool quantum mechanics is and all this awesome and bizarre behavior you get when you deal with quantum mechanics, like quantum entanglement and quantum teleportation. But when you're trying to build a computer, quantum mechanics is just annoying because it makes the electrons behave in ways that we don't want them to behave. Specifically, the problem with quantum mechanics with transistors is tunneling. So what quantum tunneling means is that an electron can go through barriers that it wouldn't be able to at the level that we're used to dealing with. It's as if I were suddenly on the other side of this podium. So for example, if we had a box, and we put an electron in that box, and we say we put it in there for a reason, to store a certain bit of information, quantum mechanics tells us that once the box becomes about the same size as the electron, there is some very real possibility that the electron will just go through the wall of that box, and then once it's outside, it's gone. It's never coming back inside. And so what's happened is we've lost the information that that electron holds, and we've lost some of the energy. And we end up having to compensate for quantum tunneling by pumping more power into our computer. So if we can build a new transistor that suppresses some of this quantum tunneling, that would be great, and it would help us make a better transistor. So that's the state of computers nowadays, and those are the problems that we're facing. So now let's finally get to the meat of the talk. Let's talk about spintronics. And let's talk about how we can use spintronics to make a new random access memory. So specifically, what I'm going to talk about today is something called magnetic random access memory, or MRAM. Some of you may have heard of this. It's commercially available. You can buy it and put it into your computers. And the advantages of MRAM are that it's almost as fast as static RAM. It's almost as dense as dynamic RAM. And you have the added advantage, and if you turn your power off, you get to keep your data. So you can think of a computer where you no longer have to have the distinction between long-term and short-term memory. You can just have one memory that does all the calculations you need and stores your data without having to shuttle back and forth between 2 different types of memory. But before I can explain how magnetic random access memory works, we need to talk about spin. What is spin? So when I talk about spin, I'm talking about an electron spin. So an electron isn't actually spinning. It just behaves like it does in certain ways. So when we talk about spin, what we're really talking about is that every electron is like a little magnet. So every electron has a north pole and a south pole. So you can have the north pole on top and the south pole on the bottom, or you can have the opposite. You can have the north pole at the bottom of the electron. Usually we show which way this magnet is pointing by using a little arrow. So we would say, okay, the electron on the left, since it has the north pole on the top, we call that a spin-up electron, and then the north pole on the right, the electron on the right, since it has the north pole on the bottom, we call that a spin-down electron. So we can think of using the orientation of this spin to encode information. So for example, you can say the spin-up electron, maybe we can say that stands for 1 bit, and the spin-down electron stands for a 0 bit. So knowing this, how do we store data using spins in actual materials? Because the problem is, in most materials, spins of electrons point in random directions. So since the spins are all pointing in random directions, we can't use that to store information. But there are certain materials, specifically magnetic materials, in which all the electron spins naturally point in the same direction. That's what makes magnetic materials magnetic. All the little individual magnetic fields of the individual electrons, for some reason, all point in the same direction, and so they add up to create a macroscopic magnet. And so we can use the direction of magnetization to store information. So let's use this information to build a magnetic transistor step by step. We'll start off with just one slab of magnetic material. And here I have a blue disk, which is some magnet, and its magnetization is pointing up. Now, the electrons on the left right now just have random spin. They're not spin polarized. But if we were to apply current and pass those electrons through the magnet, the electrons have now reoriented themselves so that the spin is pointing along the same direction as the magnet it just passed through. And so we say that a current passed through a magnet produces a spin-polarized current. Now let's add a second magnet. So in this case, the second magnet is pointed in the same direction as the electron spins. And so if we apply a current again, the electrons can pass through without any problem. And that's because if the spin of the electron matches the magnetization, the electron can pass through. But now let's go back a step and have the second magnet pointing in the opposite direction. So now the second magnet is pointing down. And now if we were to apply a current, the spin of the electron doesn't match the magnetization, and so the electron cannot pass through. So this should sound familiar. This is effectively a transistor. Just by changing the direction of the second magnet, we can control whether we get an output or not. And so if we put all of this together, the way an actual magnetic transistor works is something like this. So you have two magnetic slabs, and then in between them you have an insulating region, just the same as the transistors that I showed at the beginning of the talk. In this case, the two magnets are pointing in the same direction, and so if you were to apply current, you would get an output, and so we say that this transistor is in the 1-bit state. Now the important thing about a transistor is that one of these magnets is fixed, so that magnet is always going to be pointing up. But the other one is free, which means that by using a small current, we can switch which way that magnet is pointing. And to show you how that works, I have a demo here that will show how you can use an electrical current to control which way a magnet is pointing. So what I have here is I have a wire. It's going all the way around here, through which I can apply a current. And then I have a compass needle. So the compass needle is made out of some magnetic material. And right now, that compass needle is just aligned along the direction of the Earth's magnetic field. But if I apply a current, the current will produce a magnetic field that will deflect that compass. And the compass isn't touching the wire at all. So you can see, just by applying a current, the magnet has now moved so that it's pointed more or less vertically, with the white part of the magnet pointed up. But if instead I wanted the magnet to point in the opposite direction, I can just switch the direction of the current. And so if I were to do that, now again the magnet is pointed more or less vertically, but this time now the red part of the magnet is pointing up. And so the magnet is pointing more or less in the opposite direction than it was before. Now, in this system, if I let go of the current and there's no current flowing through, the compass will just move again to align along the Earth's magnetic field. But in the transistor, once the current is turned off, the magnet keeps on pointing in whatever direction it's been switched to. So you can just use a small current pulse in order to switch the second magnet. So if we do this in our little cartoon, if we switch the direction of the second magnet, you get something that looks like this. And so now if we were to apply a current, since the two magnets are pointing in the opposite directions, we don't get any output, and so this transistor is now in a 0-bit state. Now the advantage that this transistor has over the transistors that I was showing at the beginning of the talk is we have effectively a double barrier. We have a tunneling barrier because we have that insulating region between the two magnets, same as an electronic transistor. And we have the added condition that the two magnetic layers must be pointing in the same direction in order for there to be any current going through. So we can suppress a lot of the tunneling that's happening just by adding this added condition that the two magnets must be pointing in the same direction. So this is how a magnetic transistor, a spintronic transistor, has an advantage over the electronic transistors that you have nowadays in your computer. Now, the way that these transistors are arranged in random access memory looks something like this. So you have little stacks of each individual transistor, and they're all connected horizontally over the top with some conducting material, and they're all connected vertically underneath with some conducting material. And so if we wanted to read what one individual bit says, we can apply a current through here and read what comes out here. And the only path that that current could have taken is through this transistor. And so if we read an output, we know that that transistor is in the 1-bit state. And if we didn't read anything, we would know that this transistor is in a 0-bit state. So that's how we can read a bit in MRAM. The other operation that you would want to do is to write the bit. So what you can do is similarly, by applying currents in particular ways, in the same way as the demonstration that I showed, you can switch one of the magnetic layers and switch whether that transistor is reading a 0-bit or a 1-bit. And then the important thing about this is that if I were to turn the power off my computer, those magnets will stay pointing whatever way they're pointing. So even with the power turned off, that information is saved. And so I want to finish up just by talking a little bit about specifically what my research is. So everything that I've showed you up to this point requires magnetic materials. And the problem with using magnetic materials is that computers nowadays don't really use magnetic materials. And so if you wanted to use these materials, you would have to build a new fabrication facility, and those cost billions of dollars. And you would need to develop new procedures, which take years to develop. And so for a lot of big companies, it's not very advantageous for them to switch all their processing from regular transistors to magnetic transistors. And so the question we would like to answer is, what if we could polarize electron spins without using magnets? And so what I study is something called current-induced spin polarization. So as the name implies, we're using electric fields, not magnetic fields, to make all the electron spins point in the same direction. So we don't need any magnets in order to get all the spins to point in the same direction. The problem that I'm researching is that we don't really understand how current-induced spin polarization works. So several decades ago, some theorists came up with a theory. They predicted this phenomenon. They wrote an equation for how it should work. And they said that the polarization you should get should be proportional to something called the spin-orbit coupling, which is basically just the coupling between an electron's motion and an electron's spin. But my predecessor in my group went and actually measured the relationship between the polarization and this spin-orbit coupling, and he got something like this. So you can see it's going completely the wrong way. So obviously we're missing something. So so my research now is to do more measurements, study this phenomenon in different materials, see if we can find some trend that maybe can lead us to a theory that can explain this data. And this is interesting for two reasons. First of all, our theory is obviously wrong, so we're obviously missing something. So maybe we can find some new physics and learn something new about our universe by finding a theory that matches the data. And then once we have that theory, we could maybe use this to now build a device that uses current-induced spin polarization for some future spintronic device. So with that, I'd like to thank all of you for coming, and I'll pass it on to the next speaker.
Hey, my name is Natasha, and I am an experimental physicist, and I study a system that breaks time reversal symmetry. So let's talk about first what symmetry means. So I have this flower here. This flower looks pretty symmetric, but what does that mean? So let's imagine for a moment that I shrunk myself down to the size of an insect, and I stood on top of that flower. And as I stood on top of that flower, I just sort of looked around in a circle. That flower would look the same to me at every point. So that's really what symmetry means. It means that if I perform some action on a system and the system looks the same, it means that that system is symmetric with respect to that action. And I'm going to call that action my symmetry operation. So in this case, my symmetry operation was a rotation, and the system looked the same. So that means that this flower has rotational symmetry. So physicists study symmetries because they help us understand underlying physical laws and help us explain the physical properties of things. So here I have a diamond. The atoms in a diamond form this really symmetric structure called a diamond cubic structure. And we know that because of this structure, diamonds are as hard as they are and why they are able to resist compression. Snowflakes have this nice six-fold symmetry, and we know that that's because the crystalline structure of ice is six-fold. So symmetries are a useful way to approach understanding physics. So in my talk today, I'm going to talk about how we can use this idea of studying symmetries and apply it to particle physics to learn more about the universe. So in particle physics, we have this big theory. It's called the Standard Model. It's the best description we have so far about how fundamental particles interact. And there's a lot of fundamental particles in the Standard Model, but the main building blocks of matter, the matter that we're all made out of, is quarks, gluons, and electrons. So quarks and gluons, they form together and make neutrons and protons. Neutrons and protons form together to make nuclei, and together with electrons, we get atoms. So say I'm an experimentalist, and I want to study a system that, I want to study fundamental symmetries, right? I can go straight to the fundamental particles themselves and try to study how they interact. And you can do that at the Large Hadron Collider. But me, I like to stay at the atomic scale. So the Standard Model is incomplete. And that's sort of where physics research starts, right? Because we have these problems and we want to address them. So first, theoretical physicists like Anthony, they come along and they have some sort of prediction that we can test with experiment. The problem that I want to address in physics is why there's more matter than antimatter in the universe. So antimatter is matter that has the same mass as its matter equivalent, but opposite qualities like charge and spin. And we're all made of matter, of course. We're made out of protons and neutrons and electrons, not out of antiprotons, antineutrons, and positrons. But the Standard Model doesn't really explain why there's so much more matter than antimatter in the universe. According to the Standard Model, we should have been all annihilated a long time ago by our antimatter counterparts. But of course, that didn't happen because we all are here today. So that's sort of where we want to start. So we have these theories beyond the Standard Model that can provide answers for this question. And we can test those with experiment. So as I said before, symmetries are a tool to understand physics. So let's talk about what some of those symmetries are in particle physics. So C, P, and T are big symmetries in particle physics. T stands for time reversal symmetry, P stands for parity, and C stands for charge conjugation, which is the symmetry that switches particles and antiparticles. I'm going to talk about all of these one by one. Let's start with time reversal symmetry. So I have these videos here. So I'm going to play this video of a billiard ball bouncing on a pool table. And I want you to see that if you can tell, just by looking at this video, whether or not the video was played forward in time or if it was played backwards in time. So I'm going to play it one more time. It's kind of hard to tell. We know just by watching that motion looks normal to us. There's nothing that looks weird. Well, it turns out that, in fact, that video was played backwards in time. And the forward motion video is this one. So nothing looked weird to us in that situation. So we have a process here, this billiard ball motion, that looks time reversal symmetric. It looks the same in both directions of time. So let's look at a second case here. Again, we have billiard balls bouncing on a table, and I want you to do the same thing. I want you to see, just by looking at it, if you can tell if this video was played in reverse or if it was played normally. So for this one, it's a little bit more obvious. You know that motion does not occur naturally, so that video was played in reverse. So this is a process that's not time reversal symmetric. It breaks time reversal symmetry. Now, I have a little bit of a disclaimer at this point. I'm using this example from our macroscopic world to explain a symmetry that applies to in the quantum world and in these fundamental particle interactions. So in this billiard ball case, I've been bouncing these balls on a smooth pool table. But if instead I was seeing the motion on carpet, you would be able to tell the difference. Because of the friction, the ball will slow down over time. So there's some gray area. But in the quantum world, there is no gray area. Either these symmetries are broken or they're respected. So if a process breaks a certain symmetry, it breaks it every single time that process occurs. There's no gray area. All right, let's move on and let's talk about parity. So parity we can think of as the symmetry operation that changes a system's handedness. So handedness is a property that we can see in nature. There are certain snails that form only left-handed shells, and other species that form only right-handed shells. We can also see handedness in screw threads. So the screws that we're used to are right-handed. That means that you're going to turn them to the right to tighten them. But there's also left-handed screws that you would have to turn to the left to tighten. And some of you that have been to Saturday morning physics talks may have heard of parity referred to as the mirror symmetry. So we have a mirror here. Let's see how that happens. I have my clicker in my right hand here. But if you look at the person in the mirror here, you can see that she has the clicker in her left hand. So the mirror changed my handedness. So what a physicist at this point might ask is, do the laws of physics remain the same for the person in the mirror? This is a little bit of a simplification. So let's think about what the mirror is doing. It's taken everything, all the points from my left-hand side, and it's flipped it to my right-hand side. So I've been flipped across a vertical line, or I've been reflected across a vertical line. But what the fundamental symmetry of parity really refers to is a spatial inversion. It means that my x-coordinate, my y-coordinate, and my z-coordinates, they're all flipped. So it's not a reflection across a line. It's a reflection across a point. So it's like taking an object, pulling it through a point, and back out again. Kind of like turning something inside out. So I'm going to try to demonstrate that here. I have a glove here. It's left-handed. And as you can tell, because of the thumb placement, I would not be able to wear it on my right hand. It's definitely a left-handed glove. So I'm going to try to perform a parity operation on this glove. I'm going to try to pull it through a point and back out again. I'm going to turn it inside out. Don't worry, you guys, I've practiced this. Take glove physics really seriously. So what's happening here, I've turned this inside out, and my resulting object is a right-handed glove. So my parity transformation, in this case turning it inside out, has changed my object's handedness. So you can tell that this is definitely a right-handed glove now. I would not be able to wear it on my left hand. All right, let's move on and let's talk about the last of the big three symmetries, and that's charge conjugation. So charge conjugation is the symmetry that switches particles and antiparticles. It takes your original particle and it changes its charge and its spin so that your resulting particle is the original's antiparticle. So those are the big three, time reversal, parity, and charge conjugation. And I've talked about all of these symmetries separately, but you can combine symmetries to define new symmetries, and that can be useful sometimes. I'm going to show you why that might be useful. So here I have an object. It's a set of 4 tiles, red and black tiles. And I'm going to perform some symmetry operations on this object. I'm going to perform 2 different ones. I'm going to perform a rotation, a 90-degree rotation, and I'm going to perform what I'm going to call a charge conjugation, where I switch all the red tiles to black tiles and black tiles to red tiles. So first, let's look at what happens when I only do a rotation. My resulting object is not the same as the original object. So this symmetry was broken. Now let's see what happens if I do a charge conjugation instead. Again, the symmetry is broken because the resulting object is not the same as the previous object. Now let's combine both of these symmetries and define a new symmetry where my symmetry operation is doing both of these operations at the same time. So I'm going to do a rotation and a charge conjugation. So now my resulting object is the same as my original object. And that only worked because both of those symmetries that made up this overarching symmetry were broken. So let's see if we can do that with charge parity, charge conjugation parity, and time reversal. So we have these big 3 symmetries. What would happen if we tried to combine 2 of them? So say we have some symmetry that is broken. we can try to define a broader symmetry. So say parity, we can combine with charge conjugation to define some broader symmetry, and we'll call it charge parity. But actually, just for fun, let's see what happens when we include the time reversal as well. So we want to define some mega symmetry called CPT, where you do all three operations at the same time. Well, it turns out that we do know something about this particular symmetry. We know that it is always respected. That means all of the theories that we use to describe the universe, that means the standard model and many of the theories beyond the standard model, require this symmetry to be true. In order for the theory to describe the world as the experiments describe it, this symmetry needs to be respected. And there are experiments that check to see that this is true, and as far as we know, this is always a true statement. So I've talked a lot about how you can, about these symmetries, how you can combine them, and then we have this statement, CPT, this mega symmetry, is always respected. What can we do with that? So we had this problem at the beginning, this problem of matter-antimatter asymmetry. Let's revisit that. So for matter-antimatter imbalance, we need to break the symmetries between matter and antimatter. So we need to break charge conjugation, and we need to break CP symmetry, which is that broader symmetry. And there's theories beyond the standard model that give us places to look for these processes that might break CP symmetry. So let's look at, let's take what we've learned so far. We've learned that CPT is always respected. That's a rule that needs to be true. We know that matter-antimatter asymmetry needs CP symmetry to be broken. What that means is that if we have a process that respects CP symmetry, we know that because CPT is always respected, that T symmetry must also be respected for that process. But more importantly, it means that if we have a process, or if anything breaks CP symmetry, it must also break time reversal symmetry. Because again, we need CPT to always be respected. So for matter-antimatter asymmetry, we can try to directly look for CP violating processes, and there are experiments that do this. Or we can try to look at a process that violates time reversal symmetry, because they're equivalent statements. And as you may have guessed, I do the latter. I look at a process that violates time reversal symmetry. And that process is an electric dipole moment. So an electric dipole moment in general is a measure of the charge distribution of an object. So say I have some neutral object. There might be a lot of positive and negative charges in that object, but maybe the top of the object's a little bit more positive and the bottom of the object's a little bit more negative. An electric dipole moment is a measure of that difference. It's a measure of the charge distribution. And it turns out that if you have a quantum system that has this property, an electric dipole moment, it automatically breaks time reversal symmetry. And let's see why that's true. So say I have this quantum system. It has some spin, and it has an electric dipole moment. Now, you heard Marta say that spin isn't actually an object spinning. It's a property that is related to the magnetic moment of a quantum system. But for historical reasons, we think of it as an object spinning, and this is one of those reasons. So, and that's because it's a property that will change sign after time reversal symmetry, after a time reversal operation. And that's because if you imagine an object spinning, if you play the tape backwards, it will be spinning in the opposite direction. Again, they're not actually spinning, but it's a property that behaves that way. So we have this object. It started off with its spin and its electric dipole moment in the same direction. But after we performed a time reversal operation on it, now the spin has changed sign, but its electric dipole moment was unchanged. So the symmetry was broken. Similarly, this process also breaks parity. And you'll see here, under a parity transformation, now the object's been spatially inverted. So the electric dipole moment has switched sign, but the spin remains the same. So in both situations, you started with your spin and your electric dipole moment in the same direction, but afterwards, your spin and your electric dipole moment were in opposite directions. So that means that if you have a quantum system and it has an electric dipole moment, it will violate time reversal and parity. So the experiment that I work on is to measure the electric dipole moment of xenon. And it's called helium-xenon electric dipole moment because we use helium as a tool in the experiment to monitor our magnetic field. So this is an international collaboration between Michigan, Michigan State, and various institutions in Germany. The experiment is actually in Germany, outside of Munich. And in this experiment, we try to measure the electric dipole moment of xenon. And we try to measure it with a sensitivity of 10 to the minus 28 E centimeters, where E over here is referring to the electric charge, the unit of electric charge, which is the electric charge of the electron. So this is a really, really, really precise experiment. And it's, to give some comparison of what that number, how small that number is, the size of a xenon atom is on the order of 10 to the minus 8 centimeters. So that means if you blew a xenon atom up to the size of the sun, we're trying to measure something over a distance of the size of the atom on the surface of the sun. So it's a very, very precise measurement. And there are two ways of going about measuring something this precise. For one way, you have to find a way to amplify the signal created by your electric dipole moment. For us, that signal is amplified if we apply a really, really large electric field. So we apply thousands of volts. But another way is to reduce any sort of background that could interfere with your experiment. And to do that, there's this room in Germany where there is the weakest magnetic field in the solar system over this 3-meter by 3-meter room. And this environment reduces the any external magnetic field by a millionfold. So that's the Earth's magnetic field, that's the magnetic field created by your electronics, even the magnetic field of your bodies, to the point where the residual magnetic field in the room is really, really small. So to summarize, physicists created this really artificial, unique environment that does not occur naturally on Earth to do a high-precision measurement of a process that violates time reversal symmetry in order to learn more about why there's more matter than antimatter in the universe. I don't know about you guys, but I think that's pretty cool. So thank you all.